Hey everyone, my name is Venerin, and in this video we're going to talk about a large language model that is using state-space models instead of transformers. The new model is called Mamba, and we are going to take a look at a fine-tuned version of that called Mamba Chat, and we're going to compare the results from Phi 2 from Microsoft and compare that to Mamba 2. Also, we're going to have a look at the original paper of the model and see why Mamba is a bit different compared to other large language models. Let's get started. Mamba is trying to address one of the biggest computational inefficiency of the transformers architecture, and that is the quadratic time complexity of the input when the attention is going to be computed. So in this case, they're using these selective state space models in which they're actually trying to do the same thing in a linear time. So in a sense, you can now get much larger inputs and still pay only linear complexity or computation time for the input compared to the quadratic time that you need in order to compute the attention from the transformers architecture. So this is a very large improvement, if you will. And here in the paper, that is called Mamba Linear Time Sequence Modeling with Selective State Spaces, you can see that they're actually integrating these novel ways in order to compute these models. And in this case, they're creating an end-to-end neural network architecture without attention mechanism or multi-layer perceptron blocks, which is something that the transformers library or architecture is always using. And the result of that it is that Mamba can do inference that is 5 times higher throughput than the transformers architecture. And again, it is linearly scaling in the sequence length or the input of the model. And its performance improves on real data up to million length sequences. So these are very large context sizes. And one of the output of the benchmark that they're providing within the paper on language modeling are Mamba 3 billion parameter model outperforms transformers on the same size and matches transformers twice its size, both in pre-training and downstream evaluation. So it looks like the Mamba architecture is performing very well. And one of the more important things with this architecture, it is that it doesn't lose its efficiency, at least not as much as the transformers library. And there is a benchmark that is we're going to have a look at on that topic. I think of those types of models as an expansion or an upgrade on the previous recurrent neural nets. And instead of computing all of the previous steps within those types of architecture, here you're using just a single structure, for example, a matrix that is actually holding the complete hidden state from the computation. And this is essentially the key point in which you're not doing any quadratic computation, but just linear pass through your architecture. And the hardware aware part of this diagram is suggesting that the architecture is using two types of memory from the GPU, and the more speedy one or the faster one is called the SRAM here, and the slower one is called the high bandwidth memory on the GPU. And the difference here is that this state is actually stored in the faster memory, so you can essentially do faster computation on that one, and your model's parameters, which is the large part of the memory that you need, are actually stored on the slower type of the GPU. So you can think of this as a RAM memory and then an HDD memory, something like that. And the state is, since it is actually much more, should be much more easily accessible, read through or write to, it is stored on the faster but more expensive memory. And then the rest of the computation is also stored in the slower memory, the HBM or the high bandwidth memory. So in this sense, they're actually creating a very optimized hardware-aware algorithm that they claim that can easily 2 or 3 or 4x your inference speed. This is one very important evaluation from the paper. And this chart right here is the Mamba performance of this model, and this is the sequence length that we have. And as you can see, other models and architectures are vastly getting lower and lower accuracy as the sequence length is increasing. But the Mamba architecture is actually performing at a constant pace, no matter the sequence length. Of course, we need to get a bit more context and have to test this in practice. But again, from what I've seen thus far, this seems like a very different thing compared to the Transformers architecture. And again, another one chart from the evaluation right here. I'm going to show you for the scaling context. This is something that is, again, very interesting, fine-tuning accuracy on DNA classification. So we have very, very long sequences. And here you can see that the Mamba models are actually increasing in accuracy with the sequence length. Again, this is something that we haven't seen at all, but we've seen the other way around with the transformer architecture. So one takeaway from this is that if you have larger sequences, I mean, like really large compared to what ordinary, let's say Llama 2 or Mistral or any of those models are using. For example, if you have very long documents or DNA sequences, something like that. The version of the Mamba model that we're going to use is called Mamba Chat. And in our case, this is the original Mamba 2.8 billion parameter model that is fine-tuned on 16,000 samples from the UltraChat dataset. I have a Google Colab notebook that is using the free tier from the Google Colab, and we are running a T4 GPU right here. So the first thing that I'm doing inside this notebook is to actually install the causal conf 1D library that the Mamba SSM is actually using under the hood. So these are the up-to-date dependencies from both of those projects. And after that, I'm essentially fixing the CUDA NVIDIA paths for the model to evaluate and use the correct CUDA library versions. This is directly taken from the original Mamba Chat notebook. And after that, I'm doing some imports. I'm going to check the device. As you can see, we're using a CUDA device right here. And then I'm going to essentially print that we're using a T4 GPU, the maximum memory that I can use in gigabytes, and then the used memory right now. And then I'm going to load the Mamba Chat model from the Hugging Face. And these are the answer start and answer end, let's say, special tokens that the model is using. And I'm going to set this as an end of sequence token to the tokenizer, which is going to be loaded from here. Since the tokenizer itself doesn't have a chat template, I'm going to take the one from the Zephyr 7B beta. This is again taken from the original Mamba Chat notebook. And I believe that they're essentially using this chat template as well. And then we're actually loading the Mamba language modeling or language modeling head model from this, again, this repository from Hugging Face. Then I'm loading this on a CUDA device, and then I'm loading it into a floating 16 point. So one important thing right here is to note that the actual model is roughly 5.5 or 5.6 gigabytes of storage. And when I get the model, the first thing that I'm doing is to check the parameters. As the authors have said, this is roughly 2.8 billion parameters, slightly less. And when loading this model, at least in 16-bit floating point, you see that the model is taking roughly 5.5 gigabytes of GPU memory. So this is very good compared to what you might load into Llama or Mistral. Of course, this model is 2 times smaller. So first thing that I'm trying here is to get a prompt to work out, and the prompt is what is the meaning of life. And since this is essentially using the format from the Zephyr, I'm going to create this message from the user, and then I'm going to pass in my prompt. So next I'm going to apply a chat template to the messages, and this is essentially the tokenization that we get from this prompt. and then I'm using model.generate, and this is essentially how this is done. And here you see that this model actually takes roughly 29 seconds in order to generate this, which is, yeah, that's not a small amount of time. And this is the response. The meaning of life is a philosophical question that has been debated for centuries. It is a question that has no definitive answer, but is often interpreted as the purpose of reason for which we are on Earth. It is a question has been explored by philosophers, theologians, etc. Yeah, a topic that continues to inspire challenging people. I would say that this is a very quite alright response for a small model. And the end here, you can see that we're using end of text. So this is the special token that we're using to end this prompt, the output. So I'm essentially writing this function that is called extract response, which is going to essentially take the text from here to before the end of text ending. And I'm just looking through the string, as you can see here. And this is just the text that we are getting. Okay, next I'm going to create this helper function in which I'm going to essentially encapsulate everything that we have thus far, but I'm also going to add a system prompt if one is given. Otherwise, this will not be added to the messages. And yeah, essentially do the inputs, generate the outputs, and then run the output through the extract response and return that as an output. So this is the first prompt that I'm giving. What are the pros and cons of ChatGPT versus open source LLMs? And here you can see that the wait time is roughly 24 seconds, which is much faster compared to, I believe, the Phi 2 that we had. Yeah, and these are the pros. It is starting ChatGPT open source LLM. The cons, again, the same structure, ChatGPT open source LLMs, But you can see that we have a repetition here and here. Is a chatbot can be used for automated customer support, for instant and accurate responses to customer queries. So you see a high form of repetition. Maybe if you are adding some sort of repetition penalty, this can be fixed. But I essentially took those parameters from the Google Colab notebook. Not sure if, again, repetition penalty is going to help, but you might try that on your own. What is the most iconic dish that Slavics prepare for Christmas? The next prompt, of course. The most iconic dish that Slavs prepare for Christmas is the Slavic Christmas Eve dinner. Not sure what this exactly is. It typically includes a variety of dishes such as roasted meats, potatoes, cabbage. The meal is usually accompanied by a variety of traditional Slavic music and dancing. Well, can't really agree with that one. I'm not sure, maybe I should Google that, but definitely in my house, this isn't the case. But yeah, roasted meats, yeah, something that we do. And this was a very fast response, only 3 seconds. So this model appears to be working quite fast on some of the prompts. Then I'm asking to present itself as a Dwight Cage route and write an email to offer a subscription for a paper supply for 1 year. It did that in 12 seconds roughly. And yeah, I would say that the email is all right. It is pretty generic, but as a starting template, it looks really reasonable. Of course, it didn't include anything specific to what something that Dwight Schrute might say. So this is a bit disappointing, but at least it looks like that the output is very well formatted and it does the job for that. I think that Phi 2 did a much better job on this one compared to this model. Next, I'm asking for a $10,000 investment advice. And this is essentially the output that we get. Again, 22 seconds. Pretty fast on a T4 GPU for 3 billion parameter models. And this is the list. Index funds, mutual funds, savings accounts, bonds, real estate, stocks, crypto, private equity, gold, real estate, and then small let's say, warning or advice overall. This looks all right. I mean, yeah, probably a nice start. Then I'm trying to calculate the answer for this, and yeah, you can see that this didn't get the correct answer. Phi2, I believe it got the correct one. The response time is very fast, but still incorrect answer. And then I've asked it to think step by step, and again, the response was incorrect. Again, fast, but incorrect. So next I'm trying to write a function in Python that calculates the square of a sum of two numbers, and it gave me a response with a sample output. But again, the function is incorrect. And if I take even the function and pass in the a and b from here, 5 and 7, you see that the actual output is different to what the model is telling me that is going to be the output. So interestingly, this function is not correct. I'm not sure why this is the case, but it's not that good on coding. At least this fine-tuned version isn't. Next, something that Phi2 totally blocked out on, and I've asked it to write a Python function that splits a list into 3 equal parts and return a list with a random element of each sublist. And this is essentially the output. This is copied and pasted from there. I've added the import random since this wasn't added. And I've printed the left, the middle, and the right part from here. And from the input that is 1 to 9, a list, it essentially split the list correctly, at least in this case. But then when tried to choose an element from here, it did this strange zip. So what it essentially did was to take from the first numbers 4, from the second column 8, and then from the third column 9, which is not exactly what I had in mind. Probably with a better prompt, you might get a better result. But at least as far as I understand this prompt, this isn't exactly correct, but still much better compared to Phi2, at least in my evaluations. Then I've asked to analyze this tweet by Elon Musk, and I've asked it what is the meaning of this tweet, do sentiment analysis, rewrite it in the words of Marcus Aurelius. And Phi2 did a very good job on this one, while here the Mamba chat completely blocked out actually. Yeah, it just started repeating over and over the tweet itself. Not sure if those marks are something that it is bugging it, but again, exactly not sure why this is happening, but not a correct answer at all. And then I've asked this in order to get, let me show you the table itself actually. This is the table that I'm passing in a markdown format, and I'm essentially asking it to get me the reading comprehension for the Llama 2 7 billion parameter model, which is essentially 61.3. And in this case, this is extracting from this table, again, the same that I've shown you. And it is very confident to say that this is actually 37.5, which is exactly the number for code evaluation for Llama 2 70 billion parameters. I'm not sure if there is anything else with such a number, and at least I can't see it. So yeah, I don't think that it did a good job on that one as well. The Mamba model looks very interesting. I'm really impressed with the inference time that we got from the Mamba chat model. The correctness or the performance of the model on accuracy wasn't that good, but the Mamba chat fine-tuned version of the Mamba model might need a lot more training in order to get much better responses. So hopefully in the future, more Mamba chat-like version of the model is going to be available for us to try. It looks like that those types of model might be a very nice way to fine-tune your own large language model for specific tasks, for example, for classification, sentiment analysis, data extraction, etc. It would be really interesting, again, to have a look at those types of model, how do they handle very large inputs. So for example, you might want to try those types of model with very large chat histories, something that you can't really do using the transformers architecture, at least this far. And one very important note was the evaluation of the sequence length and the performance of the accuracy of these types of models. And it seems like that the sequence length or the window size does not affect the accuracy of the model, which again looks very promising. And yeah, we will need to test that to have a look at whether or not this is truly the case in the real world. Thanks for watching, guys. Please like, share, and subscribe. Also, join the Discord channel that I'm going to link down into the description, and join ML Expert Pro Bootcamp, in which you can become an AI engineer. Thanks for watching, and I'll see you in the next one. Bye.